So yeah, I'm going to be talking about some kind of novel structured concurrency solutions that our backend team has been using to kind of tame the growing complexity of our application. So if you haven't heard of us, we are a premium ad-free privacy-respecting search engine with about 15,000 customers doing about 300,000 searches per day. You can check out our site, Kagi.com. We have a whole bunch of info there. Has some examples of our search results, and you can see our live stats as we grow. Very cool stuff. So I'm going to get right into the Crystal stuff to give you kind of a high-level idea of our stack. Currently, our backend consists of about 70,000 lines of Crystal in what I would call kind of a 3/4 monolith scheme, where a large majority of our code is kind of in a single application, but we break out some things into microservices that might need like some dedicated resources and such. We have a focus on server-side rendering because our whole product works without JavaScript. So that part of it's kind of important to us. And we're also using software like Postgres and Redis for persistence and caching. But in this talk, I'm primarily going to be focusing on the core of our application involved with actually building your search results, which consists of a lot of decision trees and concurrent task wrangling. So hopefully that sounds cool. So here's a very basic example of how you might visualize a search flow. Starting with the user's query, we will fan out to a few data sources concurrently. These could be internal indexes, external indexes, third-party APIs, and so on. And we'll wait for all those results, collect them, do some post-processing like filtering, re-ranking, and other personalization, and render those all to the page. And then we're done, right? So if you've used Crystal's concurrency primitives a little bit, you could probably model this really easily. Just a channel that takes an array of results, and we kind of stream those into kind of a single array, and then we render them. Pretty simple. But now let's change the requirements a little bit. Say we have a new source D that we want to trigger sometimes based on the results of A, and then collect those with the rest as before. We can adjust our code for the kind of source A fiber to add a trigger check. Lost my place here. Add a trigger check and then send those along the same channel. But you notice there's a little bit of a bug here. If we decide to not send those results, then this will kind of hang because it's expecting 4 results, but we only gave it 3 sometimes. So that's not great. There's several ways we could fix this or approach it differently, but we can just fix it one way by adding a new channel for just the extra D results and checking it afterwards, remembering to close the channel if the trigger fails. So that's great. So some time goes by and requirements change yet again. This time we want to take the results from both D and C and based on some other condition, retry C with different inputs or otherwise just forward the results from D alone. This is getting quite complicated. From this little simple example here, you can imagine this kind of ballooning outwards. And it doesn't stop there. We can imagine needing to handle things like timeouts and exceptions. We kind of have to be vigilant about exceptions disrupting our control flow, because kind of the worst thing that can happen is, because of some uncaught exception, the user gets a blank page. Ideally, we want to design our network such that it's resilient to, sometimes as data source is not available, we still give the user some results instead of absolutely nothing at all. So that's far better. So how did we manage? We wrote some utilities for managing concurrent tasks that help. This task box one that I wrote, it's open source on my personal account on SourceHut. Which is very similar to the future.cr shard, but it just has some extra utilities for working with multiple tasks, racing them, waiting for all of them to complete, things like that. In our current scale, we're at about 65 different data sources across 270 endpoints and about 18 workflows. A workflow being like a search, web search results, image results, video results, and so on, and different variations of those. But we find at this point that we're kind of hitting a complexity barrier where, our largest flow is about 3,000 lines of code alone, has tons of checks, rules, contingencies, and so on. And it's kind of difficult to make changes, be it either fixing bugs or adding new features. And we kind of no longer have a bird's eye view of how everything works, no longer fits on one page, and so on. So we are wondering, how could we continue to scale our application behavior and still keep the complexity under control? Could there be a better way? So one thing that helps a lot of people is diagrams. Classically, it's what engineers make when they want to communicate how a complex system works. But, after a while, the diagram itself becomes another thing to maintain. It sort of drifts away from the truth or might elide important details that you can only gather whatever information the author included before you have to read the source anyways to find that's not quite right or, something like that. But what if the diagram could be the source of truth? Full visual programming is definitely not something that we need. However, we found that a lot of our business logic is encoded in control flow alone. So if we were to try to put into words what we're looking for, you might call it a visual DSL for kind of structured concurrency. So how could we build it? So it turns out it's pretty easy. You start out with a message type, which is some data just tagged with a port name and a kind of black box interface with FIFO queues for inputs and outputs. And then a routing table, which is rules for message delivery between these components. So we'll kind of visualize that a little bit. So we have our component in the middle here that will just take some kind of message, read the port that it came in on, and send some more data along. And I'll read these from the input queue in kind of FIFO order and stream them to the output queue in the same manner. And then we have our routing table, which looks sort of something like this in concept, where we say, okay, if foo outputs a message on A, deliver it to port D on component bar, and so on and so forth. You notice here too, we have a recursive case where foo can actually send itself a message, which can be useful in some cases. Okay, so there's a few more steps. We still need something to draw diagrams with. We picked draw.io or app.diagrams.net is the full domain. But there's a bunch of tools you could use like Excalidraw and so on. And then we need to agree on some kind of syntax for the diagram, which should be like boxes for components, some kind of shapes for the ports, arrows for connections. And here's the syntax that we designed, so you have the boxes that represent components with the ports on them, and diamonds that represent higher level inputs and outputs of the system. And each component here can represent one of two things. It can either be a chunk of native Crystal code, or it can be what we call a container for a subnetwork, encapsulating it in its own internal control flow shown here. So you can see container C is a container for another lower level network comprised of component D and E, which happen to be two totally independent flows nested within component C. And you can see here how the rhombuses map up into the kind of higher level ports. Now, anywhere that we refer to component C in our diagram, it actually refers to an instance of the subnetwork, allowing us to reuse this encapsulated control flow in multiple contexts. So with the syntax looking good, now we need an interpreter. So we can draw.io, you can export the diagram as XML, which saves you a lot of time. And we use a kind of pattern matching algorithm to pick out the semantics from which we want the from the diagram for the interpreter can also be made to do some validations at this level, such as rejecting unconnected arrows, components, or linting any kind of house rule that we establish. From there, we have a few options. We can immediately load it into a runtime, which is what we'll talk about next and what we currently do. But you could export the kind of parse diagram into another format like JSON, or use the interpreter as a meta program to generate more code. But since we just embed the interpreter into our server, we'll stick with that. So lastly, the runtime is where our component interface is defined. We showed a little bit of that before, where you have a single method contract that takes a message and possibly produces some outputs. Packaged with components is also some utilities for writing finite state machines within components, which is super helpful for larger, more complex ones. And you also have some quick access to hot variables like the current request and response or the query, for instance. All of our components get kind of exported into a registry, which is just a hash map of their name mapped to the corresponding implementation. And finally, we load the routing table from the interpreter once it's startup. But for development, it could be also hot reloaded, which we'll get more into later. So we'll look at kind of like a real example of some actual code that we're using. You can see here at our kind of main top level container where the initial request enters before hitting the router, which kind of works as you'd expect. It basically sends a message on either port that matches the request path. And in this case, we'll say it's a news request. So the flow will go into here. News is a container that opens up into something like this, where we have this news page component, which ultimately is going to render the page. But before it can do that, it needs some content to draw. So we have a couple options here. Depending on the request, we can either search for news results if there's a query. Otherwise, we just load some current events, which is just like a summary of global news. And we'll follow that path further down. Here you can see some actual requests being made. We have a cache in front, which on a miss, it'll just forward the input along. On a hit, it forwards the cache data. And from there, the current events is a native Crystal component where, depending on which port it got the message on, will issue an HTTP request. You can also see some syntax here where this W will actually map back around to this right port on the caching. So just to clean up the errors a little bit. And finally, we can kind of go one level deeper in this, where we have the HTTP component, which is super simple, just has a client in here that takes a request, produces a response. And you can also see we can leave notes in here that describe some specific behavior that we want to happen, such as when an exception happens, we still produce a response with just an empty set of data. So yes. So that should give you an idea of how this works in practice, where we kind of start from a higher level descriptions of the control flow and kind of recursively dig deeper to get into more details, while at the same time acting as real code that controls how our requests are handled. Of course, when you make a more dynamic and flexible system, it often comes with a performance trade-off, which is true in this case. So we've done some optimization work to kind of try and minimize that overhead. Just to give a few examples, we do a lot of pre-allocation of network data to minimize the startup latency. We lazily initialize components so that only the components that are actually visited in your request fully allocate and initialize themselves. We also use a lot of queues. So you can imagine, if you have 50 components with 2 queues per component, like using the standard library deck, that's a lot of, sparse allocations hanging around. So we kind of brought this all under one type called a FIFO arena, where we have a single block of memory that gives out handles to logical queues within this allocation. So in effect, if you simply daisy chain 50 components and they just send one message along, we only need to allocate space for that one message instead of based on how many components we actually have in the network. And there's some other things we could look into. If you think back to my initial examples, we were just writing some spawns, it's not too far off from what's happening there. So it's not too big of a trade-off for what we get in kind of this, dynamic productivity system. So we can talk about some results this has on our developer experience. We have a high-level starting point for designing away from kind of messy details, but it's authoritative, so there's no more of that kind of diagram going out of sync with the actual code. We can kind of agree on how a system should work in kind of higher detail before implementation even starts, and then just sort of fill in the blanks. For documentation, kind of anyone can look at the diagram and get some kind of meaning out of it without knowing, much about our code or without Crystal experience. And we can also include rich media like images and formatted text alongside of it, which is really fun. Helps a lot with, you can show like an exact image of the page of the content that is generating. So really makes it easy to understand like what you're looking at. And it helps a lot with making code reuse a lot easier by creating a sort of palette of code to pick from, wrapping systems in containers to reuse them in multiple places. And the black boxing interface helps keep everything decoupled and kind of concurrent by default. Finally, I would say it results in a more playful development of our backend, where the diagram can be hot reloaded instantly without recompiling anything, and we can create a bunch of debugging tooling on top of this, such as recording backend messages, sending them to your browser console. The network can also be hot reloaded in production. As a kind of admin developer on the production website, you can upload a personal diagram to be used, isolated to your own requests, and access the same debugging tools they have locally. And we can also update the primary diagram used for all requests to kind of toggle certain code paths, fix things, or route around buggy components without having to redeploy at all. So yeah, that's kind of the big idea. This work was inspired by a lot of projects and paradigms that came from the past, namely flow-based programming from J.P. Morrison in 1970s, working on some Canadian banking software. State Charts by David Harrell is super inspiring, which presents a concurrent state machines as a powerful development language. Dracon in 1996, very cool project. It's a visual programming and modeling language developed for the Bern space program. And lastly, we have 0D, or Zero Dependencies, which is developed by Paul Tarvidus, whose Kagi's runtime is directly inspired by Paul's work. I worked very closely with him to kind of learn and explore a lot of the ideas behind it before this really kind of came to me that before I felt it's what we need to kind of push the boundaries of our work farther. So huge thanks to him. Definitely check out his blog. There's tons of interesting ideas there. And before I go, I have a couple of bonus things that have really helped us out along the way. The first is debug pages. Make debug pages. We currently have some 45 of them that dump various pieces of data like GC stats, scheduler info, fiber lists, billing events. Super helpful just to take a minute and write a quick debug page in plain HTML, a few lines of CSS, just to get some extra insight in a pinch, or to put some test code or functions just somewhere. Especially if you don't have an observability story figured out yet. Don't think too hard about it, just write a page and you can get some info really quickly. And the second is having some kind of simple runtime configuration system. With Kagi, we implemented a very basic versioned and validated key value table where we can easily add various knobs and levers to our runtime. Don't need anything fancy, just some JSON will do that you can edit, hot reload, roll back if necessary. In this example, you can see some configuration for our search layout where we just list the order that certain inline elements should appear. So what rank should images show on the page, videos, and so on. And that's about it. So if I had some advice, it would be, think hard about the essence of your problem and what idea or concept is truly important to your application, and build something that just embodies that. And don't pass up opportunities to invest in managing your project's complexity as a sunk cost, because it has a lasting effect on the quality of life as a developer and for your users. So yeah, thanks. I'll be happy to take any questions. I have Discord, YouTube, and everything opened up. So let's see. Is this open sourced? I do plan on releasing kind of the core runtime of this as open source. So the runtime, the interpreter, as a foundation of just building software. It's not specific to web development at all. You can use it for any kind of program, really. But yeah, I do want to eventually push more bits of this as open source because I think it's a really cool idea. Let's see.
Can you hear me?
Yes.
So I have a question. I think I missed one part. How does it work? You have the visual design, and that produces the code, I will guess. And you need to, when you have to change that design, how does it produce the new code? How does it interplace with the code generated?
Okay, so just to make sure I understood the question, you're asking if I change the diagram, how does it change the code that gets made?
Yeah.
So the only thing that the diagram generates is basically just the routing table. So just the rules for how messages are passed around. So we don't actually use it. Like, you could use this as a meta program to generate code, but right now we just load a bunch of rules into an array and say, oh, got a message from this, where does it go? It goes here, send it to this queue, that kind of thing. So yeah, it just has the single interface of just take a message, do the thing, send some outputs. Everything else is just in the native code. That makes sense.
Okay, thanks.
Okay, I see a question here. How does the FIFO arena work? I assume you're still bound for the GC, so it's mostly about allocating ahead of time. Yes. So the FIFO arena works by, I don't think Kevin, I will post this in the Discord because I know you're in there, but I have another diagram somewhere that shows how it works. I'll be happy to talk more about that, but it's a bit in depth for the call here. So this is all still using fibers. Yes. Yes. So I think I skipped over that, but each one of these components in the system runs in its own fiber. So anytime the network kind of diverges, you're having concurrent execution happening, no matter what it is. So, yeah.
A quick question from the room. I was wondering how you're using the Crystal type system for the kind of inputs and outputs of those blocks, if you are.
Kind of hard to hear the questions.
Sorry, I'll talk to talking to the wrong place. Yeah. Both of them. I was wondering if you're using the Crystal type system at all for the input and output, or the kind of validation of those.
Oh, okay. Nope, it's just using queues that are in memory. You very well could use this as, like, you could implement the runtime using pipes or threads and forks and processes. A lot of ways you could implement the kind of runtime and do it in a completely distributed manner. For our use case, it's just bounded in a single application, just all in memory. So yeah, just like the standard library deck is basically essentially what we use, just a custom version of that. What are the main challenges Kagi faces using Crystal in production? If you had a magic wand, what would you fix in Crystal as a language/project? Type safe equality. I've been bitten by that one more times than I would like to admit. So, hard to say exactly what exactly I would fix, but I think type safe equality actually is pretty important to me. More observability built into the language would be amazing. We've had to write like a lot of like our own like GC observability and schedule observability. I've seen a couple of things starting to crop up for that, but it'd be great to just have like the level that like Golang has. I think that would be fantastic.